Hi everyone. So in the last lesson we have looked at the key definitions of certain quantities, angular frequency, what we mean by simple harmonic motion that's defined based on this equation, also the techniques and procedures used to determine a period of frequency, for example on the mass of a spring or pendulum. This is also a practical requirement that needs to be done. So today we're going to be focusing on the solutions of the equation, how velocity can be rewritten. We already have seen that in the previous lesson, and G as well. So the graphical representation of displacement, velocity, and acceleration with time. We're also going to have a look at the energy changes taking place uh, in the simple harmonic oscillator. Most specifically the kinetic and potential energy during simple harmonic motion and the energy displacement graphs. So in the last lesson, I did mention how we can use circular motion to show how simple harmonic motion is similar to it. And you can see here that you have the x-axis and the little object that's spinning around the circle is shown as a dot on a straight x-axis depending on its position where it is, with B and A being the maximum displacement, so the amplitudes of the oscillation. So you can see that at time 0 the amplitude is the maximum. We take this side to be positive and this one to be negative. You see that after a quarter of the period, and it's quite similar to how waves behave as well here. So after a quarter of a period, the object has covered a quarter of its path, so that's a quarter of a period, and it's now in the center of the x-axis, which is 0. So this is the x position is 0 at that point. Then when it completes after half a period, it will be at its maximum negative displacement. Remember, we took this as a positive, that should be the negative. This is the equilibrium position. Now the ball is at B, so it has covered half of its path, and you can see at the graph at this point B. This is after half a period, like we said. Then after a whole, 3/4 of a period, the object has moved all the way around to 3/4 of the circle, and you can see that it's gone back to the equilibrium position in terms of the x-axis. So this is the 0, and you can see it on the graph again there. And then that same point returned back to where it started at its maximum positive displacement. And you can see that part there. So if you take this as a complete, the time it takes to complete one oscillation, then the distance from there to there should be the time. Sorry, the range between that point and the other point should be the time period. And this is when you have a complete oscillation. So now this is a displacement time graph. How would that affect and how would that look like on a velocity time graph or on a acceleration time graph? Now, firstly, before I proceed to that, is a quick reminder that if I now wanted to know at what position the object oscillating will be at after a specific amount of time, then as a reminder from previously, we saw that omega is theta over t, so we know that the angular velocity is the angle divided by time, so theta is omega t. We also proved how we used the amplitude and this angle theta to get this value, which we came up to be as x is equal to a cos theta, since we said that theta is omega t, a cos omega t. So we already proved how we can calculate the displacement after a specific amount of time using this equation. everything works out from here onwards, basically. And I will show that, even though you don't have to know every single thing, every single derivation, I will explain which ones you do need to know. It's good for you to know because you already do the maths, and it makes it easier to remember. Okay, so before we look at it in terms of the equations, we need to look at it graphically. So what we have here is the displacement time graph. You also have the velocity time graph, and then you have the acceleration time graph. So these are all time. Now, if you move if you have a pendulum, let's say, so this is the pendulum. So let's say this is the positive amplitude. So I displaced it in the positive. I displaced it in one side, which I take it as a positive displacement on that side. So what you see here is the pendulum at the maximum amplitude as positive. Now, at that position, the ball is actually temporarily stopped, hence why the velocity is 0. And we can see that from here. So it's maximum displacement or amplitude, actually. Then you can state that you have the 0 velocity at that position. That means that the acceleration will also be maximum. Now in the center, so where the amplitude, the displacement is 0, and you can see that here, you have the maximum velocity, but you have the 0 acceleration at that point. So you keep going down the graph. And then you have this side, which is quite similar to the positive side, where you have a negative amplitude fully. The velocity is also 0 temporarily, and the acceleration is maximum in the negative direction on the opposite side. Now, the concept here is that you should be able to get from one graph to the other. And by remembering at least what's going on in the pendulum's motion, you'll be able to easily check whether your answers are right or wrong. Now, if I want to go from a displacement time graph to a velocity time graph, I simply have to get the gradient from the displacement time graph. So if I do displacement divided by time, I know that's equal to velocity. So the gradient at any point, so if I took the gradient here, remember the gradient should be a flat line here because we're taking it as the tangent to the line. So that's 0, so that's correct. Then you can see that as the pendulum passes through its equilibrium position, if you take the tangent there, then you have the steepest gradient, which means this is the point that you see as the maximum velocity at that point. And if you continue the same thing, you'll notice it everywhere is going to match with everything that you see here. So this is negative gradient, so you have the maximum negative value. This is a positive gradient, so you have the maximum positive value. If you do the same thing to the velocity time graph, so if you do velocity divided by time, you know that that's acceleration, and more specifically is the change in velocity divided by time, that's acceleration. So what that means simply is that if you get the gradient at any point on this line, so here you can see is the maximum, and also it's a negative gradient, so you'll have the maximum negative acceleration when the amplitude is at its max. Sorry, when the displacement is at its maximum, so at this amplitude. You can even notice from here that is 0, so there's where you have the 0. This is the positive gradient, so you have the maximum value here, and so on. So if you wanted to go from, again, a displacement time graph to a velocity time graph, you simply get the gradient at each tangent of the displacement time graph, and you will do the same thing if you want to get acceleration time graph, then you just simply get the gradient of the velocity time graph. There's another key feature that you might have noticed from the graphs too, two of the graphs actually, this one. So this is the displacement time graph, and this is the acceleration time graph. It's like a flipped version of each other. And if you remember, that's because it comes from the fact that we have a is equal to minus omega squared x. In other words, acceleration is directly proportional to minus x, which means that it's just simply the same wave but flipped the other way around, so in the opposite direction. Also, another key point to mention here is sometimes the graphs don't necessarily always start at or have a cosine function. They could actually start from zero, the displacement time graphs, which means that they will have to follow a sine function. So instead of being x is equal to a cos omega t, it will be x is equal to a sine omega t. And remember that sine always acts from this point onwards. So that depends on where the pendulum starts moving from, basically. Okay, just to make sure you make a note down of this. This is if the oscillation starts at max displacement, and this is used when the oscillation is at equilibrium position. Also, your calculators need to be in radians mode before you do any of these calculations. So that's important. To also define some of the symbols, X is for the displacement from equilibrium position. A is the amplitude, both in meters. Omega is the angular frequency, which is in rad per second. Also, remember that we can calculate omega using 2 pi f or 2 pi over t. And t is for the time. Okay, so this is the equation that we're going to work through from, just to do a little bit of a proof. You don't need to know this, but it's useful to experience the math that you are learning. So we know that if I want to go from a displacement equation to a velocity equation, velocity is the change in displacement over the change in time. If I take infinitesimally small changes, then I can differentiate the expression for displacement with respect to time. Now, if you differentiate cos omega t with respect to time, this is a constant in front of it, so you have to multiply it out. If you've done, for example, d cos omega t dt, then that would be minus omega sine omega t. Yeah, that's it basically. That's the differentiation of that expression. So that would be a omega, minus a omega sine omega t. And since we also know that acceleration is equal to the rate of change in velocity with time, if we consider very extremely small values of changes in velocity with time, we can differentiate this expression now. Now, if I want to differentiate sine omega t with respect to time, that will be omega cos omega t. So that will be simply minus a omega times omega, which is omega squared, cos omega t. Now, if we look at our expressions that we have three expressions. We only want to look at this one and this one. So we're just simply comparing them. You can notice that a cos omega t is the same as x. So in other words, sorry, that's acceleration. I don't know why I wrote v. So acceleration is minus omega squared x, because this whole expression stands for x here. A cos omega t stands for x, so I can rewrite this as the expression that we came up for the simple harmonic motion. Now, if we do the reverse action, then this is actually the solution to this equation, but you don't need to know that. You don't even need to know these derivations, you just need to know the equations and how to use them. Okay, so firstly, for what you do definitely need to know is how to use these two equations, definitely. You don't need to know how to derive them at all. You just need to know how to use them. I know I've showed you how to do it, but that's for your own benefit and understanding. They could ask you in the exams to do it, but they, even though they don't expect you to, they could ask you slowly to guide them through it. This is how displacement varies with time. This is the equation that you should be using if you want to calculate the displacement at a specific time. And always remember that you can use one or the other depending on where the pendulum is moving at time 0. So if it's at this amplitude, you use this one. If it's at the equilibrium, you use this one. So this is an example question. It says a simple pendulum is released 30 centimeters from its equilibrium position. So that's the amplitude already. You know that no energy is created or destroyed. So if it's released from 30 centimeters, it will end up at 30 centimeters on the other side too. It completes one oscillation every 1.4 seconds. So that's another way of saying that's the period. Calculates displacement 6.2 seconds after it was released. So we know that it started from a maximum amplitude, so that we will use this equation. So that will be 0.3 meters, because we need that in meters. Cos, that's 2 pi over t, which is 1.4 times 6.2, and that's for the omega, by the way, so I use 2 pi over t. And you should get an answer of minus 0.27 meters, which basically is telling you that the pendulum should be on the opposite side of the equilibrium position from where it has been released from. Now, in terms of velocity, you don't have to know the one that I showed you before. You need to only know how to use this equation and also a simplified version of it. So we know that the velocity is 0 at maximum amplitudes. And it should be maximum, the velocity should be maximum in the equilibrium position. So V stands for the velocity and measured meters per second. Omega is the angular frequency. Measure in rads per sec. A stands for the amplitude, which is measured in meters, and X is the displacement, measured in meters too. And you can see that since both quantities are squared, the negative signs of those values are not taken into account because they cancel out either way. And also, you know that if we are at the equilibrium position, so if x is 0, then what we have is v is equal to plus or minus omega square root of a squared minus 0. So that's simply v is equal to plus or minus omega square root of a squared, and this can cancel. So v is equal to plus or minus omega a. So this is v max, basically, the maximum velocity that you will get at the equilibrium position. You already know that at the maximum amplitudes, the velocity will actually be 0, and you can prove that as well. So if you put amplitude squared minus amplitude squared, that's already 0. So anything multiplied by 0 is 0. So this is an example question. A toy bird is suspended on a spring from the ceiling. It is pulled 6 centimeters down, so that's your amplitude. And upon release, it oscillates up and down with angular frequency. So it gives you your angular frequency there. So that's omega. Calculate the magnitude of the velocity of the toy after this time. So in other words, v is equal to plus or minus so plus or minus omega, which we were given as 9.1, square root of 0.06, because we need to change that. And for x, I actually don't have x, so I need to calculate it using the other values given to me. For example, the time. So x is equal to a cos omega t. That will be 0.06 cos 9.1 times that time, 3.4. So you can see, since the velocity equation doesn't include the timing, you can use the time to find the displacement at that time and then substitute that number in there. Yeah, so that will be value about 0.0533 meters. And you should get an answer of plus or minus 0.25 meters per second. So the magnitude is this value, because it says calculate the magnitude of the velocity. Okay, so going back to the questions, we have looked at the solutions to the equation. We explained as well how to derive it, but you don't need to know it. We have looked at the velocity equation, how to get Vmax from it. And we also looked at the graphical representations to relate changes to displacement, velocity, and acceleration. The next thing that we'll look at is the energy changes. Okay, so let's consider a simple pendulum. Now, while the pendulum is moving from its maximum displacement, whether it be positive or negative, and its equilibrium position, it experiences different energy changes. One very important part is that the total energy in a simple harmonic motion will remain constant. And we assume that there are no energy losses due to frictional forces. So this is very important. If there are obviously frictional forces like air resistance or friction between this spot and wherever it's pivoted at, then the energy actually starts dissipating to the surroundings. However, if we assume that that's not the case, then the total energy will be constant. So let's assume that the maximum displacement first, the object is moved to this position and then released. Then we know that while in this position, while stationary, you can see that it's been lifted up from a certain level from when it's in its equilibrium position. So that little height change actually causes the object to gain energy in its gravitational potential energy store. So all the energy is in the gravitational potential energy store. And as it falls back to the equilibrium position, that energy is being transferred to the kinetic store of the object. So it gains kinetic energy, with the maximum kinetic energy being in this position in the Y. So all the energy is in the kinetic store at Y. So this is the Y position. With no gravitational potential energy stored at that point, because it's already gone back to where it was already. Whereas in this position X, it had all the energy was in the gravitational potential store with 0 in the kinetic store. So this stands for the kinetic. This stands for the gravitational potential energy. And as it goes to this side, the kinetic energy decreases because it comes to a stop again at the maximum displacement. So there you see that if it stops, there will be zero kinetic energy, and all the energy will be back into the gravitational potential energy store. We can show this as a graph, which is a very, very simple graph. It's this one here. So you can plot energy versus displacement. And you can draw the curves for the total energy, for the kinetic energy, and the potential energy. Now, if you focus on the green line first, the green line is the total energy. So it's flat, it remains constant throughout, whether you're from A to A minus to zero position. So the displacement of the object from its equilibrium position. And you can also see the red line, which is the gravitational potential energy. You would expect it to be maximum at maximum amplitude, but zero at the equilibrium position. With the kinetic energy now, which is the blue line, you have the opposite. You have zero kinetic energy at the amplitudes, the maximum displacements, due to the fact that it temporarily stops, but it's maximum at the equilibrium position. And if you add this point to this point, it's 0 plus the maximum value there. So that's 1, 2, 3, 4, 5. So 0 plus 5 is 5, which will give you the value from there. So if these are 2.5 and 2.5, they give you 5 as the total energy, and so on and so forth. So wherever you add the curves from, you will notice that value from each one of them. There's one more thing here. It's not that hard, but there are oscillations that take place with springs, so a mass spring system. Now you could see how it will, how it will look like vertically and horizontally in terms of the energy changes taking place, energy transfers taking place in the mass spring system. So in this case, we have the horizontal oscillating, so oscillating horizontally. If you have them horizontally, there's only two things taking place. Since you have a spring, you have elastic potential energy being stored when it's fully stretched or fully compressed. And you also have kinetic energy since the glider is moving on an air track. This is, by the way, a way of investigating it and checking it without friction. The air track is basically a 3D object that looks kind of like a triangle, a 3D triangle, like a long cylindrical triangular shape. So that has holes on it, and those holes have air in them. So you let the air in through one end, and basically the air creates a frictionless track to test it on. So if you're ever asked in an exam question, just be aware of that. So you have, for example, the horizontal one, what you have is elastic potential energy and kinetic energy involved. Now, when the glider, let's say this is its x0, this is before it moves or is disturbed to start oscillating. Now, if it's in that position, then we definitely know that there is no elastic potential energy yet, because it's not moving, it's in this equilibrium position. But that's the point where you will have the maximum kinetic energy. Now, if you move it to displace it so that it can start oscillating and you reach the maximum amplitude, that's when your elastic potential energy will be the maximum, but because it temporarily stops, the kinetic energy will be 0. And obviously that will happen on the other side as well, where you will have the maximum elastic potential energy since it stretches to that level, and the kinetic energy will be 0 again at that point because it momentarily stops. Sorry, I don't know why I wrote kinetic max there. Now, in terms of doing mathematical calculations, you can easily calculate the elastic potential energy stored. which is a half k a squared. So the equation for elastic potential energy, if you remember, is a half kx squared, where x is the extension. In this case, we replace it with the amplitude, since that's going to be the extension or compression of the spring. If you want to find the, and by the way, if this is the maximum elastic potential energy, will obviously be the maximum kinetic energy, assuming there's no energy losses. So you can easily calculate the speed of an object using this if you know its mass. Remember, kinetic energy is a half mv squared. And you can also calculate the kinetic energy at any point if you know the compression of or extension of the spring. So at any point, the elastic potential energy, so this is the maximum elastic potential energy. But if I want to know the elastic potential energy or even the kinetic energy at a certain point, so let's say at this displacement x, then you can find the maximum elastic potential energy minus the elastic potential energy at that point. So that way you can be able to get the kinetic energy of the glider at any instant by taking the energy of the total and taking the difference between the total energy, which is this expression, and subtracting the elastic potential energy at that point, basically. So you would expect the same graph as in figure 3, but in that case, the kinetic energy against x will be an inverted parabola in that case. Okay, so there's the other system that you need to know about, which is the one that if you had it vertically, a spring vertically with a mass on it. Now here you have a few more, you have one more energy taking place. So you have gravitational potential energy, and that has to do with the change in height. You also have kinetic energy, since it's moving, and elastic potential energy, since you have a stretched spring. The key bit here is to identify what's going on and when. I'll let you have a thought over that and how you come up with it, so we can discuss it in the lesson. So what are the energy changes taking place here? How would you be able to analyze them if you had to? And how would you simplify them as well? Okay, so let's just do a quick question and then we're going to wrap this up. So you have a mass of 400 grams. It forms part of a mass spring system. It is initially released from its amplitude at 10 centimeters and completes one oscillation every 0.8 seconds. That's your period. Calculate its kinetic energy 2.1 seconds after the release and determine its percentage maximum kinetic energy. Okay, so here that requires quite a bit of work. It's not just a straightforward answer. You need to calculate the kinetic energy at 2.1 seconds and then find that's a percentage for its maximum kinetic energy too. To start with, we are given the amplitude, we're given the time. We know that the only equation that I can use that involves time is the displacement equation. We saw that the velocity one is given by, is it omega squared? Yeah, omega squared, square root of a squared minus x squared. And we also know acceleration is given as minus omega squared x. So we know that kinetic energy is a half mv squared. That's the first thing that as soon as you see things like kinetic energy and stuff like that, you make sure that you write that in the equation. Think about whether you have enough to calculate it. From looking at this, I can calculate the speed if I find the position x, because I'm missing this x value here. I don't need acceleration at all. So I will start first with this equation. So that would be remember that omega can be written as 2 pi over t, so I'm just using that. And that will give me the displacement, which is minus 0.0707 meters. Then I can place the value now in the second equation. So this is the second equation. Here. So V will be 2 pi over 0.8 squared. And the square root of 0.1 squared minus 0.0707 squared. And that will give you a speed of 0.555 meters per second. So there we are, we got our speed. Now I can find the kinetic energy at 2.1 seconds, since the speed is 0.555. I'm given the mass, which is 400 grams, so that's 0.4 kilograms. And that gives you a kinetic energy of 0.061 joules. Now that's not the end of it. I first did calculate the kinetic energy at that point, but I need to find this as a percentage of its maximum kinetic energy. To remind you that we have seen that Vmax, so the speed, the maximum speed, that's the only way I can get kinetic energy max, is by getting the maximum speed. And Vmax can be calculated using what we said already. So if this is 0, that's the maximum amplitude. So we'll leave you with omega squared A. Oh, is it omega squared A? Or was it omega? I think it's just omega. Yeah, it was just omega. Sorry, do apologize for that. I should have looked at the equation again. So yeah, you have here the maximum velocity, which is just simply omega A. And that means that you just place the numbers in. So 2 pi over 0.8 times the amplitude to get V. Don't know why I wrote V squared there. So then you just place the values in, which will be 0. So you that comes up to be 0.123 joules. So if you want to get the percentage difference between them, you just simply divide the kinetic energy at 2.1 seconds with the kinetic energy max times up by 100. So that will be 0.061 divided by 0.123 times 100, which is about 50%. So you can see that there's different ways of working around these subjects depending on what quantities you're given and what you're working with. Could have asked you to calculate the elastic potential energy, but depending on what the question gives, that's the only way that you can work through it. So we have spoken about the interchange between kinetic and potential energies. And here you can notice that we didn't just talk about gravitational potential energy, but we also talked about elastic potential energy. So that's something quite important to take a note of. You might also see a bit of simple harmonic motion being linked to electric fields if possible, but yeah, they can be linked to everything. So be careful about what it means by elastic with the potential energy. It could mean electrostatic potential energy. It could mean something else as well. And we also talked about the energy displacement graphs that you need to know. And that's just about it. I hope you have enjoyed this, and if you have any questions, let me know.